All right. Happy Thursday. We're wrapping up week 3. We're going to wrap up week 3 with chapter 4. This is the last section that is on the test. So after chapter 4, this is the cutoff for what's on the test. So just letting you know that. So when you're studying, this is the last bit that you need to study for the test. And I know the first test in every class is pretty stressful. And so it seems like, because you never know what to expect. And after you take the first one, then you're like, okay, now I know what to expect. Now I know how this teacher works. And I will let you know, and I'm glad this is being recorded. I am the queen of partial credit. If you show your work and you try every problem, I love giving partial credit. It's not just all or nothing. So make sure that you're doing some work on every single problem. So that's my advice for today, because I like to give partial credit. And so today we're going to look at chapter 4. This is one of my favorite chapters. I know I say that every week, sorry. But we're going to talk about scatter diagrams, and we're going to look at something called a linear correlation coefficient. And then we're going to talk about the linear relation that exists between two variables. So before this, we've been studying like one variable and crunching numbers with just one variable. Today, we're going to take two variables that we think are related to each other, and we're going to study their relationship to each other. And then we're going to talk really briefly about correlation and causation, and we're going to find least squares, regression lines. And none of this do you have to do by hand. It is all going to be your fancy schmancy calculator and Excel, because after we do today's lesson on chapter 4, we will be taking a look at lab 3. So that's what the joy that we have today. Hopefully those of you who've done lab 2 already found it super fast and easy. I hope. And you'll be ready for lab 3. All right, so let's get going. Find my iPad. Okay, so here's some vocabulary, the other V word. So response variable, when we're dealing with two variables and looking at correlation, the response variable is also like the dependent variable. The response variable is the one that is not driving the bus. It's like one thing happens that causes the other thing happen, or that affects the other thing. This would usually be like the Y value. If you were looking at X and Y values, this would be your vertical axis. When you're graphing things, your vertical axis is the response. The explanatory or the predictor variable is the independent variable. This one is the one that drives the bus. This is generally your X value. So if I was doing like miles per hour, if hours don't pass, you don't go anywhere. So miles would be your response to time passing. So the response variable would be miles, and the explanatory variable would be hours. Say, after this many hours, I traveled this far. And so the one that drives the bus, the one that's kind of makes things happen, is your explanatory. And then the one that is like the result is your response. It is not always super clear which is the explanatory and which is the response. It doesn't always matter. It depends on your variables on which is which. And you'll see with my lab, one doesn't necessarily drive the bus for the other one. Neither one is really response or explanatory. They're equally important. So sometimes they are equal and you just have to choose one, but sometimes one of them drives the bus, and you'll see in our examples as well. So the scatter diagram, it shows the relationship between the two variables that we have. And we put them both on the same scatter diagram. The variables are related to each other. So I ask one person 2 different questions, or miles per hour, that car is traveling, and that car travels for a certain amount of time, therefore travels for a certain amount of distance. So it's based on one car. So it's measuring on the same individual. So that each individual is a point on the scatter diagram. Put my chat up. All right. Let's actually look at some scatter diagrams and some data and all that. So here we have the depth. So this is a study about drilling into rock. So the researchers are trying to determine whether the time it takes to drill a distance of 5 feet increases when you start drilling at a deeper depth. So if I start drilling 35 feet down, it took 5.88 minutes to drill 5 feet. When they started drilling at 50 feet down, it took them 5.99 feet to drill, or minutes to drill 5 feet. So it's my explanatory variable is where they began drilling. The reason it's the explanatory is because, or sorry, not the explanatory, the response variable that is, wait, oh my goodness, I just totally messed it up. Explanatory variable, the one that drives the bus is where we start digging. The one that is the response is how long it takes to drill. Because if I don't start drilling, then it's not going to take me any time to drill because I never started. So my explanatory variable is the depth at which I start digging. The response variable is how long it takes to dig. That's what I meant to say when I messed up earlier. So I'm going to show you a scatter diagram for this. So I plotted each point. So this would be one point. I would plot a point at 35 on x-axis, up 5.88 for the y. That's my first point. So each one of these is a point. So here's my scatter diagram. So things I want you to kind of notice when you look at these scatter diagrams, you can see that for the most part, as I start drilling at a deeper depth, my time does increase. You can kind of see, if I drew a line in the middle, you can kind of see that that's a positive slope. In general, it takes longer to dig if I start at a deeper depth. It's not completely true all the time. I mean, like, take a look at this point. That's kind of low. It looks like it got a little bit faster. But in general, it seems to be the case. And that's kind of what we're looking at. We'll talk about what all that means in a little bit. But just kind of looking that it kind of has an upward trend. As the depth gets deeper, the time gets longer. All right. So we have it. Here's another example. So a golf pro is going to investigate the relation between the club head speed of a golf club measured in miles per hour and the distance in yard. So once again, the explanatory variable is the speed of the golf club. The response variable is the distance in yards, because if the golf club doesn't move, the ball doesn't go anywhere. So the one that's driving the bus is how fast the golf club moves. So the golfer realized that there's other variables that could change that. So if he has a different club type, if it's a different ball type, if a different golfer does it, if it's weather conditions, I mean, there's many, many other things that could come into play. So he did the best he could to eliminate those things. So he using the same golf club every time, the same ball, the same golfer, and took a 70-degree day with no wind. So it's like the perfect day. So he's trying to eliminate those variables as much as possible. And then he measured how fast was the club head speed and how far did the ball travel. So we're going to draw a scatter diagram of this. If you printed out if you printed out the PowerPoint, you might want to do this along with me. If not, you can just kind of watch. So here on the left, I have my data. So at 100 miles per hour, the ball went 257 yards. And so each of these is our point. So I'll show you what this is going to look like. I want a red pen. So at 100 miles per hour, so I'm going to go 100 on my x-axis, then up to about 257 on my y. Doggone it. Sorry. Okay. And so over 100, 257. So my point would be about there. Next one, 102, up 264. 103, also 103 is 274. I'm just going to plot all of these points. 101. And we're going to look at how it trends. And you just have to kind of estimate where it is in between the points. And it's, as long as you're close, nobody's going to be mad at you. So I hope nobody's going to be mad at you. That would be a really weird thing to be mad at somebody about. Oops, that was wrong. See? Okay. 100, 263, that's what I wanted. 99, 258, 105, 275. All right, so I have my data on here. And once again, if we take a look at the trend, I mean, it's kind of obvious the ball would likely go further if the club head is faster. I mean, obviously he can't, I mean, even if he gets the correct speed, he can't judge things or make sure that he's not accidentally twisting his arm, or when he put it back on, I have no idea what other things would affect it, but because I don't know golf. But you can see the trend. If I drew a line through it here, it's a really bad line. But if I drew a line through my data here, you can see as the club head speed gets faster, it generally, the ball went farther. You don't have to draw the line if you don't want. I just like to do it so that I can visualize that. So this right here would be my scatter plot. Ignore the green line on that. Any questions on drawing the scatter plot before we do more stuff?
So it just means putting in all the numbers in.
Yes. Yeah. Just plotting points. All right. So here's the different types of relations, and this is why it's important. This is why I was drawing the lines on that. So we can't say that there's no relation when if it has any kind of pattern at all, but we can say something has no linear relation. Linear relation is what we are looking at here. It's what's important to us. So like this one right here, the first one, letter A has a positive linear relation because it is a positive slope. You may remember back in your algebra class, algebra 1 class, we talked about slope. Positive slope goes uphill from left to right. This has a positive slope. If it has a negative slope, if it goes downhill, then this right here would also be linear, but it is negative because it has a negative slope. As my X values get bigger, my Y values get stronger or get smaller. That's what I meant to say. So this one down here, letter C, this clearly, I mean, if you remember algebra 2 or ever took algebra 2, you can see this looks basically quadratic, but we can't say it's a linear relation because it's not. There is a relation, it's just not linear. You may not know what this one is, but this one is cubic. I just know it because I'm a math person, but this one's cubic. So it definitely has a relation. It just doesn't have a linear relation. This one right here, this one, last one, is super scattered. It's just completely scattered and random. It follows no pattern at all. So it is just basically this super scattered thing, and there's no relation at all. Not linear, not nonlinear. There's just nothing. It's just crazy. So these are the types of relations. We're going to talk about the strength of relation probably about 8 slides from now.
I have a quick question. So you said the response was just it's called scattered, or it's called just no relation?
So there's just like on C is just it's not response. I just was pointing to the graph itself, not to the response, just to the graph. This one right here has no relation because it is just completely scattered. It just is no type of pattern or anything to it. And that one almost does, but it's just computer generated weirdness. So, but it's just wild and crazy and doesn't go positive or negative or anything. It's just there. All right. Move on forward. So let's talk about positive and negative association. This is a whole lot of words. That 2 variables are positively associated when they're linear, and the dependent variable increases as the independent variable increases. So basically, if it has a positive slope, it is a positive association. That's, if you understand slope, that's probably what I would put. That if there's a positive slope, it has a positive association. Conversely, they're negatively associated when the dependent variable increases, the independent variable decreases or vice versa, or basically if it has a negative slope, it is a negative association. Anyone need another moment to write stuff down?
Melissa, I have a quick question. So back, sorry, just back one slide. You said X values get bigger and then what does that do to the Y values? They get smaller?
Okay,
I'm sorry, one more back.
right here, as my X values got bigger, my Y values also pretty much most of the time got bigger. I mean, it's almost never perfect, but sometimes it gets pretty close. But this one, you can see that the trend is upward. As you move to the higher numbers on the X-axis, you can see that it trends upward, that the Y values are also getting bigger.
Okay, so that's just for this map. That's not for all maps. That's not like a
No,
thing.
it's not for
just-
all of them. They're
Okay.
gonna look different. This particular one right here has a positive association.
Okay, thank you.
You're welcome. All right. Okay, let's move forward. I am never, ever, ever going to make you calculate this. Never, ever. I have calculated this before, but I never, ever, ever will make you calculate this. So you don't have to write this formula down. It is ugly, and it's really not that hard if you try it. And letting you know, I make my high school kids calculate this just because I'm mean like that. I make them do it once, but I'm never going to do it. But let me tell you what a linear correlation coefficient is. It measures the strength and the direction of the linear relation between two quantitative variables. So it's going to tell you if it has a positive or negative correlation. So if it's going upward positive with a positive slope, or if it's going downward with a negative slope, and it's going to tell you if it's a strong linear or a weak or moderate. It's going to tell you how strong that relation is. Frequently, even though this is the formal name, linear correlation coefficient, it is called, a lot of times we'll just call it the R value because that's a mouthful. If we were dealing with a population, we would use the Greek letter rho, but I basically never use it because if we have a population, we don't need to do this. So we only really need to do this with samples. So we only ever really use the R value. So pretty much this is the only time I will ever tell you it's the Greek letter rho for population. From here on out, all we will use is the R value. So we always just use the sample correlation coefficient. We always call it that because if we're studying the entire population, it's not as necessary to look for a lot of things because we just know it because we have the whole population. But so I will either say correlation coefficient or I'll say R value. And I think my open math does both also. They say correlation coefficient or they say R value. Right, moving on. But don't try to calculate that. Please don't. I mean, you can, but just don't. Trust me, it's a pain in the rear. So here's the properties of the correlation coefficient. There are things that I mean, if you write them down, please make sure to just like, just shorthand because it's a lot of words. I am convinced that textbook authors are paid by the word. I think they're paid by the word, and so they give you a lot of extra ones. So it's always going to be in between -1 and 1. So the R value will always be between -1 and 1. If you get an R value that is greater than 1 or smaller than -1, you did something wrong. So if R is a +1, it is a perfect positive linear relation. It is perfect if it's 1. Same thing if it's -1, it is a perfect negative linear relation. So +1 and -1 are perfect. So next, the closer it is to +1, the stronger positive relation they have. The closer it is to -1, the stronger the negative association is. See, they use a lot of words. They use a lot of words. So just write what you need. You can, I'm not gonna like drill you on this, but you will have to talk about, you're gonna have to talk about whether things are strong or weak or moderate or whatever. You're gonna have to what's the word I was looking for? Interpret. Interpret, that's the word. Okay, moving on. So if R is close to 0, there is little or no evidence of a linear relation. So if our R gets super close to 0, then there's basically no linear relation, but it can be a relation. It could be quadratic, it could be cubic, it could be any of the others, exponential, but it's not linear. So you can't say no relation, just say no linear relation. So don't ever say no relation. Say no linear relation, or you can say strong or moderate or whatever. And I'll talk about kind of ranges, rules of thumb and all of that in a few minutes. Okay, moving on. Oh, I forgot about this one. It's unitless. The R value or correlation coefficient, it's unitless. Just like our z-scores, you would just say the R value is 0.25. You don't say 0.25 pineapples per acre. I don't know, making stuff up. You just say 0.25. All right. Moving on. It's not resistant, which it's kind of like the mean. If there is a great outlier, it's going to pull that correlation coefficient. So it's going to yank it one way or the other. So it does not resist outliers. That's what not resistant means. It's kind of like the mean and the standard deviation. They can be thrown off by outliers. All right, moving on up. And here's some great, these are great examples. So A is a perfect positive linear relation. It has a correlation coefficient of about 1. And so it's perfect. These are lined up in a perfect line, and you can see it, and it is absolutely perfect. And now that I made it unperfect, I'm going to erase that. So B is really strong positive relation. It has a correlation coefficient of about 0.9. It is a really good, strong positive relation, not quite perfect, but pretty darn close. So C, now it says it's 0.4. I think 0.4 is too small of a number. I really think it's about a 0.6 or 0.7. And you'll see as you start looking at them that this is probably, I'm going to say that this is probably 0.6 or 0.7 and not a 0.4. And I've gotten pretty good at guessing what these are because my AP Stats class at the high school and I play a game where I put scatter plots up and we guess the correlation coefficient, and we've gotten pretty good at them. So letter D is a perfect negative. So notice it looks a lot like A, except for it has a negative slope. It's going downhill. So it is perfect, absolutely perfect negative. And then C is negative 0.9. So it is also negative, is really strong negative. And as I said before, I don't think that F is negative 0.4. I think it is more, it's closer to negative 0.4 than C was to 0.4. Because doesn't C look like a better linear, like looks more linear than F? F has like some outliers there, pulling things down. Anyway, I'm just splitting hairs here. So F has a moderate negative linear relation. I'm going to talk about the ranges I use in a minute, but there's unfortunately no rules exactly. And then G is really close to 0. probably not quite 0. I would say it's probably like 0.15 or 0.2, but it's very close to 0. So we would say no linear relation, or very, very weak, but you can't say no relation. You just say no linear relation. Same thing with B. B is close to 0, but you see we have a nice pattern. And there's a really nice pattern here. It looks kind of quadratic, but it's not linear, and it's not even close to linear. Therefore, we would still say no linear relation. Any questions here before I give you guys an idea of ranges?
And so like by the no relation, you mean like no positive association or negative association?
By no relation means it's not linear. It doesn't make a line. It doesn't follow a linear pattern, neither positive nor negative. It doesn't follow a linear pattern. It's not a line. Okay, I'm going to go to my other screen, and I'm going to give you kind of my rule of thumb. And so the way that I talk about determining whether an R value is strong or weak or moderate or whatever is that it really depends on what the context of the situation is. If I'm working for NASA and I'm building a rocket, I would think that 0.9 is probably not strong enough. That would be too weak for what I'm doing. I would want a linear relation that is either perfect or really, really close. If I'm putting a garden in my backyard, 0.8 could be strong. So it really depends on the context of the situation. And that's why I think that they don't like give us rules, they give us rule of thumb. So personally, if I am doing this, if I am looking at correlation coefficients, if I had an R value that is like probably 0.85 and up, I would probably call that strong. Whoops. Yep, that's strong. I would probably call anything 0.85 or higher strong. And if I'm hovering around the 0.85 mark, I might say something like moderately strong or fairly strong. Use one of those adverbs that we all love to use. And usually if you don't like firmly say this is strong, it's almost like it's too absolute, it's too firm. So if you say this is fairly strong or this is a pretty strong relation, that kind of gives you a little wiggle room there. I usually call something moderate if it is about 0.65 to 0.84. I would call this moderate. So if I would hit the 0.84, I'd probably say moderately strong. Probably 0.8 to 0.84, I'd say moderately strong. And this would just be moderate. Now, this is just a rule of thumb. This is just what I do. Now, if you said 0.8 and you called it fairly strong, I would probably give it to you. But if you said the 0.65 was a strong relation, I'm probably going to mark points off. So there's some wiggle room here. There is definitely wiggle room. So probably about 0.45 to 0.64. I call this moderate also, but this be like moderately weak. So this right here would be closer to just moderate. This might be just moderate, or it's really hard to say. So this would be like moderately weak. And I know this is like, we all like to have like rules set in stone, but probably anything from probably about 0.25 to 0.244, I would call weak. And then anything 0 to 0.24, I would call that either like extremely weak, maybe, or very weak, or say no relation. Like at 0, you're going to say no relation. 0.1, I'd probably still say basically no relation. But if I'm at 0.2 or 0.24, I'm probably going to say extremely weak, very weak, something like that. So I know that and this is absolute value. So it's plus or minus. So this would be positive or negative. And these are not, I almost even hate giving you these. I'm just trying to give you an idea because these are not the rules. If you called 0.25 strong, I'm definitely going to mark you down. I don't even like moderate for that. But if you called it, fairly weak, yeah, that's fine. If you called 0.44 moderately weak, I would probably give it to you. Cause 0.5 just moderate, I'd give it to you. It's just, you gotta be in a range where it makes sense. And I know that this is frustrating, but it's gotta be in a range that makes sense. Questions?
On the week, that's a 0.8.
No, this is the week. It was 0.44. But I started to write something weird and so I scribbled it out. All right, any other questions? All right, as soon as I leave this screen, it disappears. So if anybody's still writing it down, let me know before I go away. The screen is like scratch paper, so as soon as you navigate away, it's gone. Okay, going once, going twice, gone. Woo. Okay. Getting ready to math, and I'm so excited. I love to math. Okay. We are only doing this with a calculator. Only with the calculator. And I forgot to load my calculator. So give me a second. Let me just go TI-84 right here. I knew there was something I was forgetting. Actually, we'll do it with the calculator and with Excel, but we're not going to do any of this by hand. So no worries. I'm never going to make you do it by hand. So get out your fancy schmancy calculator, your TI-84, TI-83, TI-80, whatever. Come on. I don't know why it's decided it needs to refresh every single time. Makes no sense to me. Okay. At least it's loading, okay. Down here. On my millions of emails. Come on. You can do it. I'm going to tell if it's loading. Okay, now it's loading. Okay. All right. So you are going to go to your calculator and you're going to go to the screen, the list screen. We're going to be entering this data right here. So just to let you know, so if you decide to work ahead, this depth at which the drilling begins, this X value, you're going to put that in your L1 column. The time to drill, you're going to put these in your L2 columns. So L1 is the X, L2 is the Y. If you don't have these printed out, you can just put it in as I put it in. So I'm going to clear this out and hit Stat, Edit. And I want to clear this. So arrow up until your L1 is highlighted, hit clear and then enter, and it all goes away. Remember, do not ever hit delete, hit clear and enter. So I'm going to enter in my values. So just putting them all in, I just put in all of the X's and then go back and put in all the Y's. Be very careful not to make typos. I am typo queen over here.
I'm having trouble deleting it.
So you arrow all the way up to L1 is highlighted. So you see how my L1 is black? Then hit
Yeah.
clear, enter. Did it work?
Yeah, thank you.
You're welcome. Five, 85, 190. All right, I have my X values in. I'm just going to arrow to the right and it brings me to the top of L2. And I'll put in my Y values. And after I put them in, I always take one last look to make sure that I didn't typo. Uh-oh, see, I messed something up. Okay, I did typo somewhere. I missed one. See, 5.88, 5.99, 6.74, 6.1, 7.47, 4297. Oh, there's there's a 7.92 that I missed. Oh, well, this is why we check. There we go. All right, I'll give you a second to finish that up, and then I'll tell you what we're doing. All right, does anyone need any more time on?
Almost there, sorry.
You need another moment?
Yeah, please,
Okay.
thanks.
Let me know when you're ready.
Got it.
Okay. Anyone else need another moment? Or are we good? All right. So now I'm going to click on stat again and edit arrow over to calc. Go down to linreg AX plus B. Linreg AX plus B. Now my guess is, just a second here, that we're gonna have to do some magic. Just give us a second here. So your X list should say L1. Your Y list should say L2. If it doesn't, so to get to L1, you do second one, gives you L1. For L2, it is second L2. So, I mean, and this stands for all the other lists also. If you notice that like 6 is list 6, 5 is list 5, I do use all of them frequently. We're going to leave the frequency list blank. So we're leaving this blank. We're also leaving this one blank here. So the frequency list is if a number shows up more than once and you're trying to be, like if I had 2 different values that were 120 feet and 7.47 minutes, then I would have a frequency list. This right here, if I wanted to store this into my calculator so that I could use it for other things, I can store the equation in my calculator. We're not doing that. We're not going to do that. I just wanted to let you know what they were. I'll go down to calculate and hit enter. Now, after you hit enter, if anybody does not have an R or an R squared value, let me know.
I don't. I have
Okay.
Y, A, and B.
Okay, let's do the magic. And this is probably good to be recorded anyway. So
Okay.
this is going to take you away from this screen, but it's okay. Hit second 0, and it's going to bring up a big list of crazy weird stuff. So second
Okay.
0 brings up this list.
Mhm.
Scroll all the way down till you get to the words diagnostic on. Whoops, there it is. I just scrolled right past it. Diagnostic on, and then hit enter. And then hit enter again. And then what it does is it's going to turn that on for you. So
Okay.
once you've done,
There's so many.
I
There's so
know
many.
it's in alphabetical order.
Yes, okay, diagnostic on. Okay, so okay, then hit enter. Got
Then
it.
hit enter. Are you good? Did it say on?
Yes.
Okay.
Yes.
So now let's do it again. Go stat, arrow over to calc, go down to number 4, linreg AX plus B, and enter. Your L1 and L2 should still be there. Hit calculate, and now it should be there. Is it there?
Uh, okay, I hit calculate. Wait, let me get to calculate. All right. No, it's not
Did you,
there.
are you sure you did on and not off?
I'm sure. Let me try it again. So
Okay.
second
zero.
What was it?
Second, zero. And then go down to diagnostic on.
Okay, diagnostic on. Okay. Okay, so there's diagnostic off. Now
So-
hit enter, correct?
Do on, you want on, not off.
Yeah, it's on the on one. So
Okay.
off is on top. And then so hit enter when it's on
Yes.
there.
Hit enter and then hit enter again.
And then hit enter again. Oh,
Yes.
that's what I didn't do. I didn't hit enter again. Okay.
Okay.
So now I hit second. So now I go back to stat.
And I go stat, over to calc, and down to linreg, ax plus b. Enter, 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 enter. Calculate. Bam. It'll be there.
So go down to calculate. It's there. Thank you.
Yay. Okay. All right. So the important things that we see here, we're going to do the linear stuff, the equation later, but I'm going to explain what it is anyway. So long time ago in a land far away, we learned y equals mx plus b, and it stuck with us. Even when we didn't know what it meant anymore, y equals mx plus b was always in our heads. So here it is right here, but it's y equals ax plus b. It is the exact same thing. The a is the slope, the b is the y-intercept. This is y equals mx plus b, but Texas Instruments decided, hey, we're going to get crazy and we're going to throw an a in there instead. This a right here that it gives us, this is our slope. This b that they gave us is our y-intercept. What we're looking at right now is the r and the r squared. So r squared is called a coefficient of determination. There will be questions that ask you about this, and I'm going to explain what it means to you, but it's not super important that we're going to go into it deeply, that you will just have questions asking you about it, like what is the r squared value in your homework. The coefficient of determination, basically what it's saying here is 59.7% of the variation in drill time can be explained by the depth at which we drill. That's what it's saying. And I know that doesn't make a whole lot of sense, and it's okay, but it's just telling you what percent of the variability of our response variable can be explained by our explanatory variable. Don't worry, you don't have to explain that. The R value here is what is important. This is our correlation coefficient. This is a pretty moderate, you almost could say moderately strong correlation. It's decent. And it's about 70, it's 0.77. So there's definitely a correlation here. And if I was putting a garden in my backyard, I would say that's a really great correlation. If I was building a rocket, it would not be good enough. So it really depends on the situation. I think in the situation of being able to estimate how much time it's going to take them to drill, I think it's probably pretty good. So if that makes any sense. So our correlation coefficient, I'm going to write it on my screen before I go back there. Is, if I could actually get my pen to work, 0.77. We usually round them to 2 decimal places. It doesn't matter. I'm not going to get mad at you if you round it to 3 or 4. We just usually go to 2. All right. Questions on this before we go back to our other screen? Okay, I'm going to bump back there. So I wrote down 0.77. I'm just going to say moderately strong. That's my interpretation. So I would be comfortable making a guess or a prediction at the time and say it's going to be approximately this amount of time. And it wouldn't matter to me. I mean, I don't think they care if it's 30 seconds off, because it could be with this correlation coefficient. Not a big deal. All right, moving on. So I would like you to try this again with the club head speed and the distance. So in your calculator, the club head speed will be your X and the distance will be your Y. I'm not going to do this on the calculator on the computer. I'm going to do it on my hand calculator. And I want to see how well you do on finding that. So remember, you go to stat edit to get to your L1 and your L2. L1 will be club head speed. L2 would be distance. So go ahead and put those in there. Once you get yours, go ahead and look up at the screen, see if you got about what I got.
What were we pressing after we got both list in?
Then you
Stat
go
again?
stat, calc, and then it's the number 4 choice. Lin
Number four,
reg
yes.
AX plus B.
Thank you.
You're welcome. R's, okay, why the R is called correlation coefficient. Oh, right here. Correlation coefficient. R squared is it called a coefficient of determination, which I don't think anybody's going to ask you that, but that's what it's called. And the correlation coefficient is our R value. And I only know all this, the correlation of determination stuff, because I've been doing this a while. Yeah, no problem. Okay, how'd we do? Did we get about 0.94?
Yeah.
Okay, I
Yes.
would definitely call this a strong correlation, strong linear relation. I don't think anybody's going to argue that 0.9 about 0.94 being a strong linear relation. So I think that generally with the stronger the relation, the more confident you're going to be predicting like future values. So if I have a correlation of 0.94, I'm going to feel much better about predicting what the distance would be if I had a 106 mile per hour swing. I'm not going to go too far out though, because as soon as you get, unless you have a perfect linear relation, the further away from your data you go, the less accurate your prediction will be. But I could predict in here, like, because I don't have 104, I could predict the distance the ball would go with a 104 mile per hour club head swing. And I would feel pretty confident because I have a 0.94 R value. That makes
I did, when I was entering the information on L2,
Uh-huh.
I entered an extra number and I keep trying to clear it out and it won't delete.
So, and you tried just going on that number and hitting the delete button? If you're in the body of the list, you can hit delete. Just don't hit delete when you're highlighting the top. Did that work?
Yeah, thank you.
You're welcome. It happens all the time. I do it a lot. Right. Any other questions? Do you want me to give you a second? See if you can get there?
What does coefficient mean?
A coefficient is just like if I had like 5x, wait, see here, 5x, that's a coefficient. That's really what that is. That's a coefficient, that 5 in front of the x. And I mean, I don't know, I'm sure that there's a better explanation of what coefficient means, but it really has to do with it being a value that gets multiplied by a variable. That's really what it is, but we're not doing any multiplication, but somewhere in the grand math scheme, it gets multiplied by something to make sense of something. I don't know. So sometimes we nod our head and smile. We say, this is what it is. So this is one of those cases.
Okay, I accept.
Yeah.
Where's that, where's that calculate button after I entered all the info into the both list?
So you hit stat. I don't have that data in here, but I can show you. Hit stat, arrow over to calc, because it's this top thing here where you're arrowing to calc, and you want the 4th option.
Oh, I see. Okay, thank you, thank you.
You're welcome. Okay, going back. All right. I'm going to give you a second to see if you get that 0.94. Then we will move on. We're almost done. We got this.
I got it.
All right.
Thank you.
Hey, good. Okay, let's move on to the next one. Uh-oh, I have the. Okay, so if a study is observational, you can't say something has a causal relationship. I can't say one thing caused another, even if they have really strong correlation. You cannot say something caused something else if it's an observational study, which is what we're doing. If you're observing something happening, you can't say that thing caused that thing. Even if there's a lot of evidence that that thing caused that thing, you can't say it. Correlation doesn't equal causation. There you go. So you can say they're correlated, you just can't say it caused it. Like I can pretty much say, I mean, I won't say it because it's against the laws of stats. You could, I mean, hey, you know, the club head speed going faster causes the ball to go further. We can't say that because this is observational. I know it's terrible, but you can say that there's a strong linear relation. They're very, very, very strongly correlated, one thing to the other. I know it's weird, but it is what it is. If you say correlation, say causation instead of correlation, that is called BS, bad statistics. High schoolers love it when I say that, so I thought I would throw that out there. All right, here's a good example. The correlation between teenage birth rates and homicide rates since 1993 is 0.9987, super strong. However, we cannot conclude that higher teenage birth rates cause a higher homicide rate because the data is observational. There you go. That's the thing, and that some of these are dark. All right, moving on. Okay, there's a thing called a lurking variable. So it's something that we didn't include with our explanatory response, but it affects the relationship between the variable, or at least in fact affects the interpretation. So there are other things that can say these two things are a strong relationship, but something else had a hand in making them strong. And I mean, the teenage birth rates and the murder rates are, that's an example, but sometimes the true relationship is kind of tweaked. It's like a false relationship because two things are correlated. So here's an example of that. So when air conditioning bills increase, crime rates also increase. There's a really strong positive correlation between them. But turning off the air conditioners will not combat crime. The lurking variable is air temperature. So when it's hotter outside, both air conditioning bills and crime rates increase. So there is that other variable there. Makes sense? Right. There's a really fun website called tylervigan.com, and it gives you correlations, things that are correlated that make no sense, like things like I was like a cheese consumption was correlated with murder rate in one state. One of them was the price of margarine was correlated with divorce rates in another state. There's a lot of really funny, weird, strange ones. There's always lurking variables that make both of those change. It's just kind of weird. Anyway, we're going to move on because I don't want to keep you here too late. And besides, I'm going to go pick up a couple really cute grandbabies after we're done here. So the least squared regression line, we also call it a line of best fit. It is also, at least in some places, called a trend line. I'm going to put that on here also, because some places that's what you're going to see. It's called a trend line. So it's a line of best fit. What it does is it makes it so that every variable or every point is as close to the line as possible. So it basically like goes through the center of your data. It is the best linear estimate we can give. So it's not going to be perfect and it's not going to include every point, but it's going to be the best estimate we have. Once we have that line, then we can use that equation so that we can make predictions. And that's kind of what I was showing you with the y equals mx plus b. So what we do is we create this trend line. And then we write our equation and it will give us an equation to predict things with. Let me show you how to do this. So on your calculator, once again, this is our well drilling. And since I'm not going to make you put this one back in your calculator because you have the other one in there right now. So don't delete out of your calculator. I'm going to show you with the well drilling, and then you can do your own with the club head speed. So once again, I'm going to go to stat calc. We're going to go back down to our linear regression right here. And I'm just going to go to calculate. And so here are my numbers. And there's no rule about what you round to. I usually, just because I'm weird like that, I will go to like 4 decimal places, but there's not really a rule. So this A right here, this A, that is the slope. So y equals this number times x plus this number. I'm going to write it down, and I'm going to go back to my other screen. Okay, 0.0116x plus 5.527. There we go. I wrote it down. So here's how I wrote my equation. Maybe. So I put a hat on my y because this just means predicted y value. You don't have to put a hat on your y. It's just something I'm used to doing. But y hat is a predicted value, and that's why I put it there. It's okay. You do not have to put that y there or that hat there. And I don't think that my open math does. I'm not sure. But anyway, I now have an equation that I can use to make predictions with my my drilling depths. So remember though, our correlation coefficient was only about 0.77. So I could make a prediction, like let's say that I wanted to guess to see what at 125 feet, how long it would take. I could plug 125 in for X here, and I could make a prediction about how long it would take to drill. It's not going to be super accurate, but it'll be fairly accurate. It's going to be within a range that I'm comfortable with. That makes sense. My guess it's probably going to be about 7.25, probably, based on, because this is 7.5 and that's almost 7. So I would probably guess it's going to be like 7.25 or something. I have no idea. I'm just making stuff up. So you just run that linear regression just like we did. And instead of the R value, you're using A for your slope. So A goes right with the X, and then the B is your Y-intercept. You're going to do this next one. So go ahead with the calculator and the numbers you already have in there. See if you can come up with that equation. Oh, and this is our last slide. Woohoo! Once you get yours, go ahead and look up and see if yours looks like mine.
So I rounded. So are we not rounding for this?
It's okay if you
particular one?
rounded. It's okay if you
Okay.
rounded. I just generally go to 3 decimal places, but if you rounded to 2 or 1, I wouldn't round to a whole number. But rounding to 1 or 2 decimal places is fine. There's not really a rule of what to round to. I just pick a value I like. I just figure, oh, you know what? Thousands place is a good place. It's not a rule or anything. So do whatever my open math tells you to do. That's all I got to say. So how'd we do?
I'm wondering why you have an X. I
Because
must have missed that.
So take a look here. Y equals AX plus B. So the A is slope. It's like the M and Y equals MX plus B. So this right
Okay.
here is being multiplied by the x, yes.
Okay, so we'll always put that X there
Yeah,
after
so
that.
y
Okay.
equals ax plus b. That helps.
Okay, and then I'm noticing on the top one you added, so I added, so why did you subtract on this one?
Because, I mean, if you did plus a negative, it's the same thing. I just
Okay.
think plus and negative looks awkward. So,
Okay, I
because
see now. I didn't see the
there's-
negative.
yeah. So I just changed it to minus. It's okay. You're not wrong by putting plus negative. I just think it looks awkward, so I changed it to minus. Same thing. Good questions. Anyone else?
I don't know how to make a negative number on my calculator.
Well, you don't need to make a negative number. Oh, I can't see it on here. It should take a look at your B value. Doesn't it say negative 55?
Yeah.
Okay. So you just put minus right there.
Okay. Oh my God. Yeah, got it. Okay.
That's good. But if
Yeah.
you wanted to make a negative number, take a
Yeah,
look.
how do you?
I was like, down next to the decimal, there's the negatives right there. But
Oh yeah, got it.
okay. All right.
There we go.
Anyone else?
So does this get solved or is this how it's left?
Well, okay,
If we
we
solve
leave
it,
it at this. If it asks you for a least squared regression line, this is what you get. I mean, there's no way to solve this unless I put a value in for a variable. But if now I said, use your least squared regression line to determine how far a ball would go if our club head speed was 104 miles per hour. So, I didn't mean to do that. So if I told you to use your regression line to determine, or your least squared regression line to determine how far a ball would go if the speed was 104, then I would be plugging 104 in for X. So I would do this.
Gotcha.
And then I would just plug that whole thing into my calculator and get a value. Now I'm curious. Now I'm gonna have to do it.
So if they give you a number, then you could plug it in there, but if not, it just stays how you have it at the top.
Exactly. See, now I can solve because now one of my variables has a value in for it. It would go approximately 273.47 feet, just in case y'all wondered.
Thank you.
I know you were dying to know. Like, I really just want to know. All right. Any other questions before we go to the lab? I say that like we're gonna get up and leave and go to another room. Nope. Okay. All right.
But we
So
are, okay, I need to clarify.
Okay.
We're adding B, right? And B is negative in this example.
yes, because B is negative, I just changed it to subtraction because subtracting a number is the same thing as adding a negative.
That's math. Got it.
Yeah.
Thank you.
It's all
Okay.
right.
Thanks.
You know, we're sitting here doing math at 6:40 in the evening. I don't think any of us, we've probably all had really busy days working and everything. None of us are at 100%. So there's no dumb questions. Ask all of them because none of us are at 100%. That it's okay. So don't feel like, man, I should have known that. We're all exhausted. Plus, full moon. Okay. Is everybody ready for the lab? All right.
Yes.
I like
Thanks.
this lab. This one's a good one. Okay. So this is lab number 3. And with lab number 3, we're going to create a scatter plot with a trend line, and we're going to talk about our values and correlation. So I have the worst variables. So you're going to need two quantitative variables that you think are related. So something like, I mean, you're not going to want to pull your friends, so just look up some data. I can tell you that one of my favorite places to find quick data is to just go to the census.gov. It might be uscensus.gov. The census website, real easy to find data super quick. also any kind of like football or soccer or any sports websites. Like if you go to NFL.com, you could probably find 20 games, and you can find wins and losses or whatever. Anyway, so I took imaginary friends, and I have the husband's age and the wife's age. There really is no explanatory or response because one doesn't drive the other. But I just put the husband's as the X and the wife's as the Y, grabbed 20 or 20 something fictional heterosexual couples. That's all I did. They made them up. But I just did this. We're gonna pretend I asked my Facebook friends. So my population obviously would be my Facebook friends. The variable I'm studying is ages of husbands and wives. My units would be years. I'm not interested in the data. I don't really care, especially since I made it up. You're going to talk in letter D about why you think your variables are associated. So all you're going to do is basically say, I think that most likely husbands and wives' ages are near each other. And so I think they're probably associated. If you did something like number of cups of coffee that you drink per day, or that somebody drinks per day, compared to how many hours they work, you say, I think probably people who work more hours probably drink more coffee. So you're just talking about what you think and why you think they're related to each other, whatever that is. This is not relying on a definition as much as it's just relying on why you think that they're related to each other. Does that make sense? Once again, if you got these off of a website, I want either the URL of the website, or you would say, I went to NFL.com or I went to the census website. Tell me where you got your data and how if you gathered it yourself, tell me how you gathered it. Right?
Melissa,
Yes.
for D, so you said you would write, like, for this one, you put, I think that most likely husbands and wives' ages are near each other because what? Because they're similar.
That's just what I think. It's just, I think
Oh,
that
okay.
husbands and wives' ages are usually near each other, and the husband is usually older. I think but I don't know if they really have an association. I'm just making stuff up. But if, like, for example, if you were looking at the number of, I don't know, how old somebody is compared to how many children they have. You think older people are probably going to have more children. It's just whatever they are, you need to talk about why you chose that, why you think that they're associated. Okay. And whatever that is, the only wrong answer is not answering that question as, I mean, your opinion, it can't be marked wrong. If you actually answer the question as why you think they're associated, it can't be marked wrong. Because
Okay, that helps my opinion then. Okay,
yeah,
so
it's
now
your
I
opinion.
understand. Got
Yeah,
it.
definitely. Okay. So the way we're going to do a scatter plot is you're going to highlight both your X and Y axes, your X and Y values like this. So I just pushed my finger down on my trackpad and just dragged it until all of them were highlighted. Click on insert, and recommended should give you a scatter plot, because I just want a basic scatter plot. Take a look at that. If you don't have the recommended, is it right here? It's right here. This one right here. And you would just choose the one that looks like a basic scatter plot on the left. Don't choose any of these funky weird things right here or these weird bubbles. Just choose a basic scatter plot. That's all I want. Okay. Now I'm going to move it so that it's in its right spot, make it bigger, make it all that. Also, I would say don't try to make it pretty until after you add stuff to it. Or make it pretty first and then add stuff to it. So if I wanted to make it dark, or I want to make it, I don't know, change my colors. I might not like blue. I want some weird reds, whatever you want to do. Change all of that before you add stuff to it. Then we're going to add chart elements. We need X and Y axis titles. So primary horizontal, primary vertical. Okay. So your vertical one is going to be the Y value, the second one. Your horizontal one will be the X one, it'll be the one on the left. So this one would be husband's age. I gotta actually delete that out of there. husband's age. I'm going to make this bigger so y'all can see what I'm doing. And then this one right here. Come on. I hate when this does this. Why did I do that? Don't do that. Okay.
Is
Why?
the horizontal one the Y or the X?
The vertical one is Y, the horizontal one is X. And then and whatever your title wants to be, as long as it's related. Spouse ages, I don't know. Ages, I don't know, making stuff up as I go along. Okay, so this is all well and good, but we still need a trend line on here. I need the line of best fit on here. Thank goodness I don't have to come up with that on my own. I'm going to add another chart element and look down here. We have trend line. We want linear. We are only doing linear, but I'm going to go to more trend line options because I want this to open up. So more trend line options. I go to linear. Down here at the bottom, display the equation, display the R squared value. These two things, display the equation, display the R squared value. Because now, get out of this, take a look. I have my equation and my R squared value. I moved it. I'm going to make it a little bit bigger because I want to be able to actually see it. And you could change its color. See, right up here is where I made it bigger. Up here at the top left with my font. You can change the font if you want to. Go crazy. Uh-oh. It's thinking about it now. No. Okay. I just did something it didn't like. All right. So
Before you go any further, could you, so I got lost at more trend line options. What did you, what did you click to find that more
Okay.
trend line
this
options?
second here. So I gotta go back and see if it'll let me. Come on. Okay. So add chart element. When you click, go to trend line and go to more trend line options. I don't know if it's going to let me back there. Is it? Okay. I want linear. Go down here. You want to display the equation. You want to display the R squared value. Display the equation and display the R squared value. These are the two things I
Thank you.
want to put on there. Yes. Is it not going to do it again? Is it? Yes, it did. I got it. Okay. Delete. All right. So it doesn't give us our R value, which is really unfortunate, but it doesn't give us our R value. So we have to calculate that. So what I'm going to do is in this box, I'm just going to type R equals because I'm kind of like labeling it. I'm going to make this a little bit bigger so we can see it. I just typed R equals because I want to be able to see that that's what that is. And then here I'm going to math. I'm going to put equals square root SQRT. And then I want the square root of 0.8616. Because this is an R squared value, if I take the square root of it, I'm going to have my lovely R value. And I'm going to make this bigger so we can see. Okay, so my R value is 0.928. It's amazing how fictional data can give you nice, pretty strong linear relation. So the one thing that Excel doesn't do for us, it won't tell us if we have a positive or negative relation when we take that square root. It's going to just give you positive. Mine is clearly positive because I have a positive slope. But when you are doing this, if yours has a negative slope, make sure that you indicate when you discuss how strong your relationship is, make sure that you indicate that it is a negative relation. Because mine is clearly positive, but if yours has a negative slope, make sure you mention that it is negative, that it is going downhill. So in F, what I want you to do is I want you to talk about how strong your association is between your two variables. And you must reference your R value. When you're explaining, reference your R value. Don't just say, hey, yeah, look, it's going up. It looks pretty strong. You need to actually reference your R value and say, my R value is 0.928. Therefore, it is a very strong positive relation, linear relation. So make sure that you reference that R value. You talk about if it's positive or negative, and that's enough explanation. Because it's 0.928, it is a strong positive linear relation. Right, that's it. Any questions?
I would like, I just, I want to have fun with the data, and
Uh-huh.
I am having a hard time thinking of good, good numbers or good, what, like, does anything stick out from other students
I
in the
mean,
past, what people have done?
I mean, some people, I mean, I've had people, I don't know, it's for these labs, I think that most people save their like fun data for their final project, because you're gonna have to have two variables you think are associated. But I mean, there's a lot of people that do things that are just do sports things, or look at, I've had somebody trying to think of things that they do. Right now I can't even think. I mean, most of it is just like census data or rainfall and elevation. Or I've had people take like just pick 20 states and look at like the median house prices and the like poverty level, or things like that. I mean, it's really I generally for this lab, people just find something easy, and then the
Okay.
final project is when they get really creative and have fun.
Okay,
However,
but so thinking ahead,
yeah,
then think of something better for the final project.
for the final project, I encourage people to do something that they're passionate about, or maybe something that has to do with their future career, because the best projects are the ones where people actually care about what they're doing.
Okay. Okay.
So I'm probably going to give the final project assignment to you. It's usually either late week 4 or week 5. And that way you have plenty of time to think about it. There's like 3 due dates, because I used to just give just turn your final project in and not give interim due dates. And what happened was people would not even start collecting data until like the day before it was due.
Mm.
And things were rushed. So basically, to kind of help you not procrastinate, I give you 3 different due dates,
Okay.
and it's helpful. Okay. Any other questions directly about the lab?
I do really quick. So the only thing I didn't understand is when you went and you put in R equals and then you typed in.
Okay.
Can you do that one more time if
Okay,
it'll
so
allow
all
you
I
to do
did,
that?
this is just words. This is just typed in R equals. There's no math here.
Okay.
I just wanted to
Okay.
say R equals. So here, I typed in equals, and then as soon as I start typing it, you'll see SQ for square root. See how right here it just SQRT? That's just
Yes.
square root. And then I
Okay.
took R squared value, which is up here, and I just typed that in because I want to take the square root of the R squared value. And then, except for the fact that I forgot the decimal point, I didn't want to do that. Let me try it one more time. So equals square root 0.8616. Close my parentheses and hit enter, and it takes that square root for you.
Got it. Thank you.
You're welcome. Anything else? Anything else for on the recording? I'm going to stay on the recording and let you all know real quick though. Next Tuesday, this coming up Tuesday, because it is the date that the test opens, this is kind of my pattern, what I do. And I will not be teaching new material. Instead, I will be here from 5:30 to 6:30, and it will be office hours. So you just drop in if you want some help at answering questions on the test review, or you have other questions, and you can pop in if you want. It's not required. I just hang out here. I generally will like read a book or something until somebody shows up and answer questions. So it's just drop in for that hour. That way it's kind of office hours to get a little bit of help before the test. So new material not until next Thursday. All right, I'm going to turn off the recording